of people had trouble with the two spools of ribbon. So you had one of them that was tied in place, or nailed in place, I guess, and still free to rotate. And then the bottom one was allowed to drop. And so you had ribbon coming out of both spools and the bottom one falling downwards and rotating at the same time. And the question was about the acceleration for the bottom one.
And so, to me, the key really seems that both of them have mass, because that makes it a step harder than just the bottom one rotating. And also, I feel like that's going to really guide the SIM.
So let's think a little bit about the SIM then before we get started. So the system, do we want to treat them separately or as one system?
Separately.
Why do you say that?
So if we take both of them as the system, then we're not going to learn anything because there's nothing acting on it.
Yeah, I mean, there's gravity pulling down on this guy, and then there's like an unknown normal force here from the pin that's holding it in. Yeah.
You would still have to know the interactions in the middle to find how the center of mass is moving.
And then the next thing would be the interactions, right?
Yep.
Okay. So we know gravity is pulling down on the bottom spool of yarn.
Yeah. And then you just have the rotation of these two. They have masses, and then the tension is going to cause both of them to rotate.
And because the tension is uniform throughout the rope, that means they'll have the same rotation, right?
Yeah, if they had different masses or different sizes, then the moment of inertia would be different.
There we go.
And so then we'd have to worry about like how far out is this tension pulling on them and all that kind of stuff. But because everything's identical for the two of them, same tension means same angular acceleration.
So the interactions just match up with the models, right? We have translation and then rotational.
Yeah, so the gravity will give us the net force and dynamics model. There's your translation part, and then the rotation part will need the net torque and rotational dynamics.
So why do we actually need both of them? Because one of the last problems we did, we found out that if something has a force on it, then even if it makes it rotate and translate, the translation is just described by the force you put into it. So why doesn't gravity just drag the whole thing down at a regular gravity acceleration?
What do you think?
I think it's because there's also a force pulling it up, right? We have the tension force pulling up, so that's going to take a little bit away from gravity. So that's actually a good check on our answer, right? We expect it to be about the acceleration of gravity, but just a little bit less. So we can use that to check our answer.
Yeah, it doesn't matter whether gravity's pulling down on the center of mass or tension's pulling up over on this side or whatever. It's all about adding up the total force, and it doesn't matter where it's applied in terms of the translation part. Now we also do have the rotation, so we do have to worry about that too, and that'll definitely come into figuring out how to get the tension.
We have rotation and translation, and just use those 2 or 3 equations to find the tension and therefore the translation.
Yeah, I ended up needing 4 equations for it as a whole. So there was for the force part, you do your force balance, right? So sum of your forces equals mass times acceleration. I did that for the bottom one. There's no point in doing it for the top one because the top one's nailed in place anyway.
Yeah.
And then I needed to look at the rotation for both of them, so that was 2 different equations.
Okay.
Even though they had the same angular acceleration like we were talking about, I still did it as 2 separate items. Set it up that way to start with.
Okay.
And then the last thing was relating how far the bottom one falls to the amount of ribbon that comes out. Because the total distance that the bottom one moves is equal to the amount of ribbon that comes off of the spools.
And so that's just going to involve some kinematics and geometry.
Yeah. A lot of the kinematics was overkill for this. I did it through the angular accelerations. So you have A equals R alpha as a fairly general thing. And so when this one was accelerating downwards, the amount that it spins tells me how much ribbon comes off of it, and then the amount that this one spins tells me how much ribbon up here. So the acceleration of the bottom one was angular acceleration of the bottom times its radius plus the angular acceleration of the top times its radius, and then that gave me the linear acceleration for the bottom.
Due to the tension.
Due to the tension for the top one, and yeah, the rotation happens due to the tension on the bottom one. Yep.
And then we can just subtract that from G, really.
Yeah, once you find that tension, then you can subtract it off from mg and get your total acceleration for the bottom piece.
But when you go back and think about it, it still seems really, really complicated. Like,
I don't know, it's a situation where a lot of things match up nicely. All the stuff that I was looking at this at the beginning thinking, oh, well, what if this one spins faster? What if that one spins faster? It turns out they don't.